So we saw that variables have types which determine what we can do with them. Now let's look at how variables are actually stored during the execution of our program. So normally we have variables to store intermediate values during our computation, and they come in three broad categories. The first are variables that are local to the function in which they are declared. So these are, for instance, local variables that you use for iteration, for x in L in a Python program. So x would be a variable which goes over the elements in the list, and you don't want this x to clash with any other x. Then you may refer in this function to variables which are declared outside, so called global variables which are declared in enclosing blocks which call this function. And finally, you might have dynamically created data like a linked list where you add nodes. So you only have a variable which points to the first element in the list, but the internal elements which are pointed to by internal pointers, the next pointers in the list, are also part of the storage that your program uses. So the first thing that we need to understand is when a variable is meaningful in a program. So when is a variable available for our program to refer to? So this is called the scope of a variable. So let's look at this code. So we have a function f on the left which uses a local variable x. And in the course of computing that loop, it calls another function g. And g in turn uses another x in order to range over the numbers 0 to m minus 1. So clearly the x on the right is not the same as the x on the left. So the x in f, even when f is executing, temporarily goes out of scope. That is, when we go from here to g and back, when we go into g, the x which is defined in f is no longer in scope, it's no longer available for use because there is another x inside g which blocks it or masks it. On the other hand, the x which is there in f doesn't disappear obviously, because we have to then go back in the next iteration and go to the next element of the list. So there is storage allocated for x when f starts, and this storage will persist until f ends, even though in between that x is not available to us when we go to g and come back. So this is called the lifetime of a variable. So the lifetime of a variable tells us from the time that we allocate space for the variable, how long that space is available in memory without getting destroyed. So the lifetime can, as we saw in this example, exceed the scope. There may be periods when the lifetime of the variable is valid, that is, there is still storage for that variable, but because of the way our code is written, it is not in scope. So this is sometimes called a hole in the scope, right? So there is a period during the lifetime of a variable when we cannot actually access it because it is not available to us. So how do we now manage this different kinds of variables with respect to the memory so that we have no ambiguity about which variable we are referring to and which variable is in scope? So remember that each function needs storage separately for its local variables. We need an x to be stored for f in the previous example and a different x to be stored for g. The way this is usually maintained is to provide space for the variables of each function in what is called an activation record. So let's consider our usual definition of factorial, the recursive definition of factorial, which says factorial of n is 1 if n is 0, and otherwise it is n times factorial of n minus 1, the typical recursive definition. Okay? So if you want, you can write def factorial n. So you can say if n is equal to 0, return 1, else return n times factorial of n minus 1. So this is the typical function that we are going to deal with. So inside this function, there is a variable n, right, namely the parameter. So here is the activation record when we call factorial of 3. So factorial of 3 will have n set to 3. So that's what this line is saying. And it's going to eventually need the value of factorial n minus 1, but I don't know what that value is until I execute that function. So I have a space to store factorial of n minus 1 in my activation record, but at this point I don't have a value for this. So now factorial of 3 is going to call factorial of 2. So this will create a new activation record in which factorial of 2 has its value n equal to 2, and it in turn is going to call factorial of 1, for which it doesn't have a space. Now what happens eventually is that factorial of 1 will call factorial of 0, and factorial of 0 will return 1, and so on. So how does that process work? So when the function exits, this will go off the stack, right? So this activation record will be removed because factorial 2 is no longer active. But different functions may have different amount of space. So we don't know in advance what is the size of an activation record. So we need to know where the previous activation record is. So this is maintained in each activation record through what is called a control link. So when I create an activation record for factorial 2, I also add this link which tells me where the previous activation record from where this function was called begins. So that when I go back one step, when I finish factorial of 2, I know now what is the beginning of the activation record that is on top of the stack. The other thing is that we need to populate this space, right, factorial of n minus 1, and this value comes back from the function which just exited. So I have a return value link, right? A return value link tells me where to take the return value that I produce in this function and store it in the previous activation record. So therefore, an activation record contains space for the local variables, and then for bookkeeping, you have to keep track of where the previous activation record was so that you can restore it when you exit, and also where to return the value that you're going to return from now and store it in the previous activation record, because usually it will be stored somewhere in the calling function. So this is how this memory stack works. So now with respect to this stack, we can talk about the scope of a variable. So the scope of a variable basically says that if it is local to a function, it will be the topmost function. So if I'm talking about n, for instance, at this stage when I have called factorial of 2, then the scope of n is this activation record. So I look at the top of the stack. Now if I had a global variable, in this case I don't, but supposing there was a reference to x in this function, then and I don't find an x in the local activation record, I would then go back and say, okay, let me see if there is an x in the function that called me. And if there is no x there, then typically here there will be another control link and you will go back to the function that called factorial of 3 and so on. So you will keep going outside the scope. In some sense, there is an enclosing scope in order to find it. So that's how you can keep track of both global and local variables. So typically in a Python kind of a situation where you have a main function which starts, then those values will be at the bottom of the stack and they will be reached by a sequence of links from whatever function is currently active. And in this case, the lifetime of a variable is determined by whether or not it remains on the stack, right? So the lifetime of this n equal to 3 is as long as this activation record for factorial 3 remains on the stack. Now, if at a later point factorial of 3 exits and it's called again, that will be a fresh factorial 3 activation record and a fresh n. So that will not be in the same lifetime as this n. So one thing we mentioned there is that n was actually stored on the stack as an argument to factorial. So when a function is called, the arguments are actually substituted for the formal parameters in the function definition. So if I have some function like this, for instance, f, which has two arguments a and l, and then I set up some code where I set x equal to 7 and my list and my l equal to 8, 9, 10, and then I call it, then what this means is that x is going to play the role of a in the function and my l is going to play the role of l in the function. Right? So I have to substitute the values that I pass as arguments for the formal parameters in the function. So as we saw before, these parameters are part of the activation record. They are populated when the function is called and I create the activation record. These values get initialized. So I can actually think of it as having an implicit initialization. Right? So I can say that I have like these two lines at the beginning of my function which populate these values in my activation record. So it's as though I set a equal to x and then I set l equal to my l and then I run this code. Okay, so it's almost as though I have a copy of that code with these initializations as assignment statements at the top of my function. Now there are two ways in which these values can be passed from the argument to the formal parameter. So the first one is called call by value. So here I just copy the value. So here I would take this 7 and I would say that I would assign a fresh location and call that fresh location having the same value 7. This is what happens in Python in what are called immutable variables, right? When I do an immutable assignment in Python, I effectively get two copies of the value so that if I update one value, the other one does not get changed. On the other hand, I could have what is called call by reference. So in a call by reference situation, so this my list is pointing at this point to some location which has 8, 9, 10. And now when I say L is equal to my list, this is also pointing to the same location. So I am pointing the parameter variable to the same location as the argument variable. Therefore, if I make a change to L inside the function, it also makes a change to the my list outside the function. So in this situation, you can have what are called side effects, right? A function can update something inside which will have impact outside. And this is usually used for large structures like lists and dictionaries, where A, it is inefficient to copy everything and make a fresh copy of the whole list of the dictionary inside the function, and B, very often you do want side effects, like you want a function that can sort a list, or you want a function that can reverse a list. So you would like the resulting list to have that property that you have executed inside the function. Now one thing one has to be careful about is that one cannot change the reference. One can change what the reference is pointing to. So I can take this list and I can update it in place, right? I can make this into say 9, 9, 10 by replacing the first value, okay? But if I take this L and make it point to another thing, I create a fresh list by doing an L equal to something inside my code, inside the function code, this will actually change what L is pointing to, and now what the list outside and the list inside are pointing to are no longer the same. So this is something that one has to be wary of when passing by reference. So you can pass by reference, but if you expect the change to be reflected as a side effect, then inside you can only make so-called what Python calls mutable changes, right? You can only update in place, but you cannot reassign that reference to point to something else. A typical example of this happens when you want to insert a value at the beginning of a list, right? So you cannot make the head of the list point to the new node. If you remember, you have to make the new node, in some sense you have a list, and you have this, so you will create a new node and then you will do some plumbing. So you will copy the new value here, you will make this the old value, and then you will basically route your list like this, right? So these are the kinds of things that you have to be a little careful of when you do call by reference. So speaking about lists, what happens to the values which are created by functions which do things like insert a node in a list, right? So clearly the storage for this new node is created when the function runs. But if it is part of the stack, then it will also be destroyed when the function exists, and this is not what we intend, right? So we intend that this node that we create inside the function that adds a node to a list should persist after the function exits. So therefore it cannot be on the activation record, because if it were on the activation record, then it will go as soon as the function pops. So this kind of data is called dynamically allocated. So this is data which we create not as part of the names that are there in our program. So statically declared data consists of all the variables that we actually use in our code. So in a language like Python, statically declared means that we actually name the variable and assign something to it. In other languages like Java, it means that we actually declare it upfront, say this int is, I is an int, or x is a float, and so on. So these statically declared variables will be defined on the stack. But through these statically declared variables, I can create new storage which is dynamic. It is created as the function runs, but it doesn't have a name of itself. It's accessed through a statically declared name. So this storage is usually called the heap. Okay, this is a separate piece of storage from the stack. It's called the heap traditionally. Now one thing to be careful is that this has nothing to do with the heap data structure that we have studied in the data structures course. So this is not to do with priority queues or anything. It's just a disjoint storage from the stack, and it has no particular structure. It doesn't, like the stack has this last in first out structure, the heap has no particular structure. So conceptually you want to store the heap disjoint from the stack. So our stack, remember, is growing downwards the way we have assumed. Right? So we have memory, and the memory is a sequence of locations, and the stack is growing from one end. So what we do is we allocate space from the opposite end for the heap, so that the heap will not intersect with the stack. So we will not have any confusion that the stack kind of overruns the heap at some point. So the main point is that the storage in this location, whatever is inside the heap, does not get deallocated. So the stack will basically, now the top of the function, the last function, if it pops, then this part of the stack will be removed from the memory, so that those variables will no longer exist. But remember that even though the heap persists in memory, we need to have a way of getting at it. So we would need to know, for instance, if there is a list in memory here which has been stored, we would need to have an access to it through a variable on the stack. So if we don't have any variable on the stack which points to the element on the heap directly or indirectly, then that variable on the heap is effectively unusable for us. So this leads us to another question. So when we had a stack, the memory management was easy. When I create a function, when I call a function, I create an activation record, put it on the stack. When the function exits, I remove it from the stack, and correspondingly all the storage that was allocated for that function disappears. So there's no problem. It's a clean system where I know when I add the memory and I know when I remove the memory. Now in a dynamically created data point like we saw, it is created in and put into the heap, and we have to know that we have an access to it. Otherwise we wouldn't know whether this part of the heap is in use or not. So periodically, of course, we do also want to get rid of data from the heap, right? So for instance, if I have a delete node function, right, then the deleted node is now dead storage, because I would typically have a list in which I have some links, right, and then I want to delete this node, and the way I delete it is by making this point directly to the node after it. So I bypass the node in the link structure. So now there is no access to this deleted node anymore from my variables in my program. On the other hand, at some point I had taken the storage by asking for it. So I need a way of telling the system that this storage is no longer being used. So how do we do that? So in some languages like C, for instance, you do this manually. When you ask for storage, you call a function, and then when you return the storage, you call another function which frees that location. So you have to make sure that you free everything that you don't use, and if you don't free it, right, then that storage will be assumed to be in use. And this leads to what is called a memory leak. So you should think of your memory as a tank, right? So think of the free space as a tank of water, right? And every time you ask for something, you open a tap and it gives you some water. So your water is your storage space. So a memory leak corresponds to saying that your storage space is getting emptied out without being replenished by being restored. So if you don't restore free space to your memory, then eventually your memory runs out and you have a memory leak. This leads to obviously performance penalties because the system slows down. In the worst case, your system can actually grind to a halt. This does happen with large systems which are run for a long time. For example, browsers, even operating systems which are not written properly can start getting resource hungry as they run, and then sometimes you have to restart in order to restore the performance to its usual level. The other thing that can happen with this manual memory management is that you have freed P by doing this, but maybe you kind of forgot, or your code is such that there may be situations after this where you believe that P is still pointing to something valid and you make an assignment. Now, depending on how type safe your language is, that assignment may or may not be allowed. And if it is allowed, then it may be that you assign some value to a random piece of memory which you don't have access to. So therefore, working with explicit memory management can be error prone, and it's difficult very often to keep track of things systematically, especially in large bodies of code. So the alternative to memory management being done manually is obviously to do it automatically, and this is what is called garbage collection. So languages like Java and Python actually use automatic garbage collection, and what this means is that they periodically check that storage is not being used and return it to the free space. So one common way to do this is what is called mark and sweep. So this is a little bit like a reachability check in our graph. So we have at any given point, if our program is running, so on the stack, right, we have a bunch of variables which our program is currently using, and they are all pointing to different places in the heap. So what we do is we go through this stack and we access every place on the heap that is reachable from something on the stack, and we mark it. At the end of it, anything which is on the heap which is not marked is not reachable from the stack, so we can assume it is free space. So all the unmarked cells can be returned back to the free space, and then we can resume the program. So this is a simple way to do automatic garbage collection. Now the problem with this, of course, is that this has to be done while you are running the program periodically. So this garbage collector will run in parallel with your actual code. So this means that when you are running Java or Python code, there could be unexpected slowdowns in your code because your code has to be suspended. Remember that it is not very reliable to be running your code and doing garbage collection at the same time, because there could be some contention. You might be asking for some data and the garbage collector may have marked it as free, and then there will be some inconsistency. So having what is called a concurrent garbage collector which runs while your program is running is a bit tricky. So you actually have to stop the program and then run the garbage collector, and this means that your program could unexpectedly run slower because the garbage collector ran at that particular time, and then next time it ran faster. So the performance can be erratic. So you have the advantage that the programmer does not have to keep track of this memory explicitly, but you have the disadvantage that the program performance is subject to these slowdowns which are not within your control. So to summarize, what we have seen is that in order to manage our memory, we have to talk about how these variables are stored in memory. So variables have a scope, which is how long the storage allocated to them is available to us in the memory, and a lifetime, the scope tells us whether we can access the variable or not, and a lifetime which tells us how long the storage persists. So it could be that because you have called a function which hides a variable might still be alive in the sense that storage may still be on the stack, but it may not be in scope. So for functions and local variables declared in functions, we have these activation records which are stored on a stack. So every time you call the function, you put an activation record on the stack. Every time you exit a function, you pop it. And for this, you also keep these control links and return value links to tell you where to go back after popping it and where to return the value that you just created. And for values which are defined dynamically, like new nodes in a list and so on, so these are not values which are pointed to by variables on the stack, and also they should outlive the stack. The function that creates a list should not destroy the node after it exits. So these dynamic storage area data values are stored in what is called the heap, which is a disjoint piece of memory. But here we have to be careful about how to restore free space back from the heap. If we do it manually, we could have some problems with memory leaks and other issues. On the other hand, we could use automatic garbage collection, which is what Java and Python use, which is convenient for the programmer, but it might have performance penalties.